pleasure to open this afternoon session. Our first speaker is Evelyn Yoczira Torres, who is originally from Mexico. Currently, she's Queen Mary at the University of London, and she will tell us everything and more about geometricalization of spectral triples for entities. The room is yours, the floor is yours. Take it.
Okay, thank you. Hello everyone. My name is Evelyn. Thank you for allowing me to be here. The work that I'm going to present here is joint work with my supervisor, Shan Majid. I'm going to introduce a perspective of spectral triples, not in full, but I'm going to say a little bit more later. First of all, I want to introduce a little bit of the formalism because not everyone works exactly with the same. So in here, I'm not working with sister algebras. I'm just assuming that I'm working with an algebra, an unital element, and also with the star structure. I'm gonna give, of course, the star is related because we're working over C. I'm gonna give it the function that is gonna work like the differential, and I'm gonna work with one forms using the map D that is gonna satisfy only the Leibniz rule. Also, I'm gonna try to have, or not gonna try, I want to have a differential graded algebra, and therefore I'm gonna ask the map D to behave in this way, to behave with the graded algebra like this with the wedge product. I'm gonna assume that this set of one forms is generated by this. I'm gonna require, because I'm assuming that the algebra that I have is non-commutative in the best case, the only case that I want. So I do want to have, if I have the possibility to have a special element that commutes with everyone, this element is going to be labeled by theta. If theta exists, it's going to be satisfying this relation with D and the elements of the algebra. And when this happens, I'm going to say that the algebra I'm working is inner. Then, because I want to recover quantum Riemannian geometry, the next thing that I'm going to want is to have a metric that is involving here. Now, not any metric per se. I want to have a specific definition for this, and I'm going to call it the generalized quantum metric. And this is going to be an element of the tensor part of the one form times the one form over A. And it's going to be given, it's an element here, but if it's given, I want to ask to have an inverse map for this. Now, this probably looks a little bit more complicated, but basically G is a map, and then I'm looking for the inverse map or the inverse matrix as the map inverse that I have over here. And of course, the relation that I start to have, as long as I keep accumulating elements in this framework, I want to make everything compatible with everything. So now that I introduce the metric, I want to make it compatible with the wedge product. And I want to point out that also this satisfies, just by the definition of wedge G equals to 0, that this thing is going to be central. Now, all this framework is followed by the work of the book that is in the book, all their papers. So my supervisor, Shan Majid, and Woodbex in the book that is over there. Now that I have the metric, I'm entitled, allowed to work a little bit in connection, because this is non-commutative. I have a definition on the left. I have a definition on the left and on the right. And if you spot it, of course, this is the way that they interact because this is non-commutative, but also the relation between the left and the right part are basically given by this sigma mapping here. Now, this sigma map is very important. Is among of the things that I have, it is one that is being defined uniquely. So if the way that I give the definition for the bimodular connection, if this map exists, it's going to give uniquely determined by this expression in here. This map is very important, but most of the times, what I want to do with this map precisely is to do the flip part, which is the best part, the first part that we have in here, and also have other terms related in here. But I want to emphasize in here that many times with the algebras or the work in progress that we have in certain specific problems, we assume for simplicity that the braiding, this map is called the braiding map, it's only the flip map, because with this, it holds with everything, and sometimes we ignore, not that we ignore, but we simplify our life a little bit. The way that this framework is defined allows me to define something that is called the partial definitions, partial derivative, sorry, and if there exists, it satisfies this definition. This is a little bit of the framework, but it exists. I'm going to use it later, so that's why I'm saying it. Now, as we introduced at the beginning, we have an algebra that it is related with the starter structure. So we introduce more elements in the game. So we are going to give a compatibility structure for this. So for this, I say explicitly what I want for the start map to have. And then I'm going to say exactly how this is going to be related with the elements of the basis of the algebra and also the map D. I'm also going to say how it relates with my special element, which is the theta. I'm also going to say how it relates with my connection. And if this happens, it is going to be called star preserving, and it's going to satisfy the relation. So with this, I am able to construct with the quantum Levi-Civita connection. And in this framework, due to the specifications that we have even a more weak version for that. It depends the problem that you have, the Levi-Civita connection that you're going to have. So now, for this, we are going to use basically the regular, which is torsion-free, with this definition, and metric compatibility with this definition. So if I find this, if I lucky enough to have this definition satisfied, then I can basically stop in here and then ignore the weak version. But not all the time the moduli of solutions that I obtain in the Levi-Civita connections are going to hold. Sometimes the only solution that are hold is the trivial case, and I'm not interested because it doesn't give me more information to work. But most of the time, if this doesn't work, I can work with the weak version of this. So the metric compatibility and the contortion expression that I have in here is just a skew-symmetrized version of the metric compatibility. That is first introduced in a paper of the 99. So once, if I have the quantum Levi-Civita connection, then I'm going to be able to work or to say that I have the weak version. The other way is not true. And the thing that we want to highlight, or I want to highlight, that this thing, it is not unique, unlike the classical case. So once we have this, I'm also saying that the way that we work is we assume the dimension of the set of one forms, and then with the relations that we have that we need to satisfy for the torsion-free, for the metric, with the braiding, with the connection, and so on, we are going to describe exactly how the torsion, how the connection looks, and of course the torsion. And usually we assume that we have this relation in terms of the basis, and then we solve to, or we try to find what is exactly this gamma expression. I'm going to use this expression later. That's why I'm introducing it here. And then with this, I have more or less the basis. Now, the good part, I want to say, is what I understand with the geometric realization. So I'm not constructing the full description of a spectral triple with this framework. The analysis part is missing. We took a very simple one, so it's not the full thing. So if we want to be more a little bit more precise, we are working in the algebraic level or in the tensorial part level. Nevertheless, this framework, it is very interesting because we explicitly use later the definition that we have constructed, or the reason why I took some of my time to explicitly express the Levi-Civita connection is because I'm going to use explicit expression that I have before in order to give a more particular representation, not representation, expression for the spectral triple that I'm working in here. So I'm going to restate a little bit of what I want. I want the unital algebra. I want all the framework that I have before. I want S, my spinor bundle, which is going to be bimodule element. And then I'm going to assume the dimension of the space. And then with the relations that I have, I should be able to give an explicit expression of the elements that I have in here. Therefore, it depends the algebra that you take, the explicit expression that you're going to have for the EI and the SI. assuming central basis too. So I'm going to recover this definition that it's, the one that you're going to see here is the explicit definition that I took from the book, but it is also given in papers. I think the first one is Cohn's Marcoli in the 95, something like that. Well, not something like that, that one. And then I want to introduce in the same way as before how I understand this. So I want to have a Clifford action, which is gonna give me this expression. Now I wanna have a bimodule connection, which is related with the S or the spinor bundle. And notice that the only thing that I'm saying in here, or that is saying in here, is basically I'm giving like the expression of how this action is applied on the elements of the basis, and I'm giving some Ci alpha beta or elements, which are matrices or constants that I have in here. I'm basically just describing the elements of the basis because I assume that they were free, and then I'm gonna then later solve all the constrictions and restrictions that I have in order to have an explicit definition of that. And of course, I have the braiding. The braiding, if I have an expression for the connection, it is given and solved. And I take, as I said before, the most simple expression for this expression that I have in here. Not all the time I'm respect to this, but I can assume that. I'm also assuming that I'm taking the map following or the sketch of Cohn's actions, the antilinear map. And of course, I'm gonna start after this to start to relate everything that I have in conjunction. So this is basically the 4 most important elements that I have, and then I'm start to relate this with the other expressions. So the reality condition, it is related the elements of the bimodule connection, the basis, with the antilinear map or the Church conjugation map, then the compatibility, and then I'm start expressing everything of the Clifford action with the antilinear map, and then I'm missing one relation, which is, and no, it's not missing, the braided it is involved, the braided it is involved in here. So as we have a spectral triples, we have even or odd cases, and therefore if we have an even case, we are going to have the expression that we have in here for the specific extra relations that I have for this extra bimodule map. Once we have this, so I want to say that the relations that I'm going to express until here are basically taking the tensorial part or the algebraic part of the Cohn's definition, so doing nothing else. And then, of course, the relations that I have from the epsilons are given by this map, by this table, sorry, to give even or odd relations. But then what is different in here? So what is different is I want to introduce a geometric conditions. These geometric conditions comes from the quantum Levi-Civita connection, explicitly related with the map of the Clifford. So C and Si and S are given. So it's exactly the basis for the Clifford action, the bimodule connection, and the braiding. So that's the first thing that we have in here. So I'm having an expression. So this is only in the spinor bundle, but this right-hand side in here, this gamma ijk, it is related with the explicit expression of the Levi-Civita connection, the basis of that. And then the remaining part that I have to have is the relation with the Clifford action in here. So with this, if it satisfies, it gives me an extra condition to satisfy with the other, with the basic algebraic part, but also considering in a very explicit expression to satisfy the Levi-Civita conditions in here, in a very explicit way. And also notice that I'm introducing for the first time the metric that we are gonna have. Then I have with this the definition of associated Dirac operator, and with this I have the definition. So this is a very basic definition. I'm not doing anything special. I'm taking the most simple case that I can have with the positive linear functional defined like this, and the trace. So I'm taking the most basic part, and I think I killed myself in the time. So I just want to say that the matrices, the very last picture that I want to show, so I give the relations, so taking deep, and then the final solution with some restriction that I have in here it's gonna, so the Levi-Civita conditions are gonna be in here, basically. And the last condition that I want to show is, no, this one. So this is the direct operator with many restrictions that I didn't say, but yeah, okay. Yes, so thank you.
Thank you so much.